Okay. So today we're going to be talking about two lessons, like I said, vertical and horizontal asymptotes. And we're also going to be talking about concavity, which is where the graph bends, and terminals. Just do this. So Sebastian is here. So I got Leanne is missing. And I think that's it. Leanne is here and Rabia is not here at all. So vertical asymptotes. So this is just basic review from last year. So a rational function is a function defined as f of x is equal to p of x over q of x, where p of x and q of x are both polynomials, and our denominator q of x cannot equal 0 because we get our graph undefined at that point. Rational functions are undefined at values of x for which the denominator is equal to 0. To sketch these functions, it is necessary to determine what happens to f of x as x gets closer to the values of which f of x is undefined. So for example, we have our graph f of x equal to 1 over x. So we just have that rational function. So who can tell me what my domain of 1 over x is? What would my domain be? What is my domain for f of x equal to 1 over x? Come on, guys, I know you know this. This is from last year. Yep, so it's x is the element of all the real numbers such that x cannot equal 0. So we've learned our graph of 1 over x would look like this. It's like a butterfly with the middle being the body. So now let's figure out what happens to the limits as x approaches 0 from my right side. Okay? As x approaches 0 from my right side, which is from here to here. So at 1, it is 1. At 0.1, it is 10. And at 0.001, it is 100. And now we also need to look at the limit as 1 over x approaches 0 from my left-hand side, which is from here. So as you can see, at -1, it gives me -1. At negative 0.1 gives me -10. And then -100. So we can come to the conclusion that the line x is equal to 0 is an asymptote or vertical asymptote of the graph y equals 1 over x, okay? Because we have as our limit approaches 0 from the right-hand side of f of x, we get my y values approaching positive infinity, because that's what my values approach. And as x approaches 0 from the left of f of x, it is approaching negative infinity. So basically, we can call these the behaviors around the vertical asymptote, which is x is equal to 0. Okay, so you guys understand this? This is review from grade 12. And review from limits. So it's two birds in one stone over here. Is everybody following so far? Perfect. Like I said, we're going to take some baby steps and just work through this slowly. All right. So in summary, a rational function in the form f of x is equal to p of x over q of x. Let's see who just entered. I got to mark them away. Perfect. That's fine. You joined on time, so I'm just going to fix the attendance right now. All right. So no, it's necessary to check that P of A cannot equal 0. If Q of A is equal to 0 and P of A is equal to 0, then there is a hole, an asymptote at x is equal to A. So for example, if I have my factored rational function as x plus 2 over x minus 1, all divided by x plus 2, I can just cancel my factors x plus 2 and x plus 2, which means that there is a hole at x is equal to negative 2, which also means that my graph is discontinuous at that point. So f of negative 2 is undefined, and a hole in the graph at negative 2 and negative 3 would exist, which means there is no vertical asymptote. So to evaluate what y value our hole happens at, we sub in negative 2 for our equation, and it should give us negative 3. So to determine the behavior near an asymptote, whether the asymptote is approached in an upward or downward direction, one-sided limits for f of x as x approaches a must be evaluated. One of the limits must be true. So we would have f limit of f of x as x approaches a from the left is equal to positive infinity, or the limit as x approaches a from the left is equal to negative infinity. So you can have this as our left limit, and I'll show you what that means in the next example. And we can also have limit of x approaches a from the right is equal to positive infinity, or limit as x approaches a from the right is equal to negative infinity. This will be our right limit. Like I said, we'll see this in our next example. Or what this also means, as x approaches a, negative means from below the asymptote. And then we have, this is from below the asymptote as well. You can also understand that with that. We'll get to that soon. And x approaches a from above asymptote. We will get through that as well. So we'll have some examples where we have to figure out where we see this. No, our assignments on Tuesday. So example 1, we want to determine any vertical asymptotes of the function and determine the behavior of the graph of the function for the values of x near the asymptote. Then we want to sketch f of x near the asymptotes. Okay? So we're just going to sketch the graph near the asymptotes. So we have f of x is equal to x over x squared minus x minus 6. What can I factor my simple trinomial in my denominator? How can I factor that? Okay. So we have f of x is also equal to x minus 3 and x plus 2. Which means my f of x is undefined at x is equal to positive 3 and x is equal to negative 2. Which means that I have vertical asymptotes at x is equal to negative 2 and x is equal to 3. So let's draw my vertical asymptotes. So I have 3 over here, and let's say I have negative 2 over here. x is equal to 3 and x is equal to negative 2. So I now need to determine my behaviors around my vertical asymptote. So I'm going to have two limits, one with x approaching 3 from the right and one approaching 3 from the left, and then one approaching negative 2 from the right and negative 2 from the left. So if I take my limit as x approaches 3 from the right of f of x, so can someone give me a number that's to the right of positive 3? Give me like the next decimal point. Yeah, 3.001. If I evaluate f at 3.01, what does my graph give me? Or what does my solution give? What value? Anybody? Let me get my calculator out. You just sub in 3.001 to my original function. 60, right? So it's getting closer to my positive y values, which means that the limit of x approaching 3 from the right of f of x is going to become closer to positive infinity. Okay? So if I come from the right, that means this part of the graph is going to be increasing upwards at all times. Now, if I take the limit of x approaching 3 from the right, from the left, so let's say I have f at 2.99. What is my value of f at 2.99? It's going to give me about negative 61. Which means that it's safe to say that as I approach 3 from the left, my y values are going to be closer to negative infinity because they are going down. Now I want you guys to tell me what happens with my limit for x approaching negative 2 from the right. What does that give me? And the limit of x approaching negative 2 from the left, what does that give me as well? Let's see what you guys come up with. I'll give you a hint. Evaluate f at negative 1.99 and f at negative 2.01. So I want you to do those two on your own. Calculate, give me the limit of x approaching negative 2 from the right and from the left. Give you guys a minute to figure those two questions out. I'll ask one of you for an answer. So did anyone get a value when they evaluated f at negative 1.99? What did that approximately give me? Okay, about negative 40 at 1.99. Oh, positive 40, sorry. So as x approaches negative 2 from the right, I get positive infinity, and from the left, I get negative infinity. So this means if I were to sketch this graph out and guess what it looks like, it would look something like this. As you can see, as I approach x, as x approaches negative 2 from the right, I keep going up. And as x approaches 3 from the left, it keeps going down to negative infinity, which is what we got over here. And then my last piece of the puzzle is as x approaches negative 2 from the left, I get closer to negative infinity. So is everybody good with this example? Yeah, there's an asymptote as y is equal to 0 as well for this one. So we'll talk about horizontal asymptotes as well in this lesson. Yeah, I just made a rough sketch, to be honest. It should pass through 0, 0, though. So I'll be more precise. I'll make the thing pass through 0 in case it bothers people. There. So there would be for some parts of the graph. For example, the reason being is because we have to take into consideration the behaviors around 0 from above and below. Okay, and that's something we're going to learn in this later on in this unit. So just give me a second. We'll go through some examples, and then I'll explain how to get the horizontal asymptote for some part of the function. Because as you can see, for the left side and the right side, it appears that it doesn't cross the asymptotes, or it doesn't cross the x-axis. But later on, we'll be able to figure out how to find our horizontal asymptotes using what we know from the numerator and denominator and the degree. So there are some times where actual functions do cross their asymptotes. But that also depends on how they behave as they approach their asymptotes. So there are some cases where graphs can cross the asymptotes. So now the limits as x approaches infinity. So consider the behavior of rational functions as x increases without bound in both the positive and negative direction. So notation usually describe this behavior is as x approaches negative infinity of f of x, and as the limit of x approaching positive infinity of f of x. Recall that the graph of the function of y is equal to 1 over x as x approaches positive infinity and as x approaches negative infinity. So as x approaches all the positive infinities, it approaches a value of 0. Okay? So as I keep getting more positive x values, I keep approaching 0, but never exactly hit 0. And as x approaches negative infinity, my y values also approach 0. Therefore, I can say that my horizontal asymptote is y is equal to 0. On the next page, we'll learn how to find horizontal asymptotes, so don't freak about that right now. We're just going to continue with this concept over here. Also, it is important to notice that as the limit of x approaching positive or negative infinity of a over x, we're going to be basically using our limit rules. We can write it as a of limits of x approaching. I'm going to write this neatly somewhere else. This is way too messy. I don't have enough space. You can say this is also equal to, bring the a out of the limit as x approaches positive and negative infinity of 1 over x, where a is constant, so we know that the limit of 1 over x approaches 0, which means that the limit of a over x is equal to 0. We're just basically using rules from limits from unit 1. So, and then we can find the limit as x approaches positive and negative infinity of 1 over x to the n, where n has to be bigger than 0, so that means it has to be positive all the time. So again, if we use if we use our limit laws, we can rewrite this as equal to the limit of x approaching positive and negative infinity of 1 over x all to the power of n. And we know based off the above that the limit of x approaching positive or negative infinity of 1 over x gives me 0 to the power of n, which ultimately ends up giving me 0. So we know that the limit of x approaching positive or negative infinity of 1 over x is equal to 0. We come to figure out that the limit of x approaching positive and negative infinity of a over x gives us also 0. And the limit of x approaching positive and negative infinity of 1 over x to the n also gives me 0. So now we can determine the value of each of the following. So we have the limit of x approaching positive infinity of x over x plus 4. So when it comes to horizontal asymptotes, all you're doing is dividing by the variable and its degree from the denominator. So in my denominator, my highest degree is 1. So I can divide both the top and the bottom by x and x. Okay? Remember, to get our horizontal asymptote, we're just dividing by the degree that is in the denominator. So the next one, I have x squared. So I can divide by x squared over x squared. And my next one, my highest degree in my denominator is x squared. So again, I divide by x squared. So we can rewrite this as the limit as x approaches positive infinity of x over x divided by x over x plus 4 over x. And as you can see, these cross out to give me 1, and these cross out to give me 1. So I get the limit of x approaches positive infinity of 1 over 1 plus 4 over x. But we know that the limit of anything that is a number a over x, it is going to approach 0. So the long way to do this is write the limit of x approaching positive infinity of 1 over the limit as x approaches positive infinity of 1 plus the limit as x approaches positive infinity of 4 over x. We know that this is going to give us 0. So at the end, we get 1 over 1 plus 0, and that gives us 1, which means that the limits of x approaching positive infinity for x over x plus 4 gives me a value of 1. Which means that my horizontal asymptote is what? We found it using the limit. What's my horizontal asymptote? Y is equal to what? 1. So I have a horizontal asymptote at y is equal to 1. Now let's take that same idea and apply it to b. So we're going to take the limit as x approaches negative infinity. Again, divide everything by x squared. So 2x over x squared just gives me 2 over x plus 1 over x squared, all divided by 3x squared divided by x squared is just 3, minus 1 over x squared. So who can tell me what the limit approaches as x approaches negative infinity for 2x plus 1 over 3x squared minus 1? Feel free to type your answer in the chat. So remember, this is like a over x. This one's like 1 over x to the n, and this one is like 1 over x to the n. So what would my limit be? It's a pretty easy number. It's nothing too complicated. Zero. So 2 over x, the limit approaches 0, plus 1 over x squared, the limit approaches 0, and you get 3 minus 1 over x squared, and the limit approaches 0. So we get 0 over 3, which gives me 0, which means therefore I have a horizontal asymptote at y is equal to 0. Which means that my graph does not cross the x-axis when we have a value of 0. And then the last one, let's see if you guys can figure this out on your own. Do C and then type in your answer in the chat. So the limit as x approaches positive infinity of 4x squared minus x plus 2 divided by 6x squared plus 5x plus 1. So do what we did for A and B, and then type in the chat what your limit approaches. Okay, if anybody else has an answer, feel free to type it out. Okay, Priyanju got 2/3. How about the rest of you? Okay. So if I were to write this over, I get limit of x approaches positive infinity of 4 minus 1 over x plus 2 over x squared over 6 plus 5 over x plus 1 over x squared. We all know that these limits approach 0, so we're left with 4 over 6, which simplifies to 2/3, which means that I have a horizontal asymptote at y is equal to 2/3. So all you're doing to find your horizontal asymptote is you're taking the variable with the highest degree and dividing it by both your numerator and your denominator. It's basically another way of saying division for polynomials. So again, in summary, a rational function has a horizontal asymptote only when the degree of the numerator, okay, is less than or equal to the degree of the denominator. That's the important part. Your denominator cannot your numerator cannot be higher than your denominator. So determine the end behaviors of f of x, that is, evaluate the limit as x approaches positive or negative infinity of the function if limit of x approaching positive infinity of f of x equal to L, or the same thing when you approach the negative infinity, then the line y is equal to L is the horizontal asymptote of the graph of f of x. So now to determine whether the graph is above or below the horizontal asymptote, now I'm introduced to this idea that as x approaches to positive infinity, f of x is greater than L, which means above the asymptote. And as x approaches negative infinity, f of x is less than L, then it is below the asymptote. So we'll get into an example where we have to show that. So to check if the function crosses the horizontal asymptote, we need to solve the equation f of x is equal to L. So we have to set our function equal to the value we got our horizontal asymptote at. So for number 3, we want to determine the horizontal asymptote and state whether the curve approaches the asymptote from above or below. Also determine algebraically if the horizontal asymptote is crossed, and then sketch the function near the asymptote. So we're going to start with the same thing. My degrees in numerator and denominator are the same, which is okay. So I can divide by x over x, which means I get my limit as x approaches positive or negative infinity of 2 plus 5 over x over 1 minus 1 over x. So we know that 5 over x and 1 over x, their limits approach 0. So it means I get 2 plus 0 over 1 plus minus 0, which gives me 2, which means that my horizontal asymptote is that y is equal to 2. So I have y is equal to 2 right here, and this is my horizontal asymptote. So now I need to figure out what happens when I approach my x values from positive infinity and when I approach my negative infinity values. So I need to take a really big number that's obviously going to tell us what happens when if I am coming from above the asymptote or below the asymptote. So let's try to evaluate f at a very high infinity number. So f at 1,000. If I evaluate f at 1,000, I get 2.0007. Now, based off what we learned from above, I need to determine if that's greater than or less than 2. Is 2.0007 greater than or less than 2? greater than 2. So this is greater than 2, which means that my limit as x approaches my positive infinity of f of x is equal to 2 from above. Okay, this means from above. Which means that my graph as it goes to the positive infinities is going to be approaching my vertical asymptote from above. Because it's above my horizontal asymptote. Now I need to take a really big negative value. Let's try negative 1,000. When I evaluate f at negative 1,000, I get 1.993. Is that greater than or less than 2? Less. So this is less than 2, which means that my limit as x approaches negative infinity of f of x is equal to 2 from below. So my graph, as we get more towards my negative x values, is going to approach my horizontal asymptote y is equal to negative 2 from below the asymptote. Which means that I'm going to have something that's coming this way because it's approaching it from below. Now, number 3, I need to check if my horizontal asymptote gets crossed. So I need to set my function equal to my horizontal asymptote, which is 2. I get 2x plus 5 over x minus 1 is equal to 2. Simple algebra cross multiply, so I get 2x plus 5 is equal to 2 times x minus 1. 2x plus 5 is equal to 2x minus 2. 2x minus 2x is equal to negative 2 minus 5, which means 0 is equal to negative 7, and we know that that's not true, which means that my horizontal asymptote is not crossed. If that gave me an x value, then I would have to solve. Then I have to plug in, I would have to sub in for x and figure out at what y value does my graph cross the horizontal asymptote. Does anybody have any questions about this as of yet? Pretty straightforward. All right, perfect. And then I have my last question. So oblique asymptotes, I know this wasn't introduced to you guys in advanced functions because we were told not to teach you it. But I'm going to introduce it here. I'm not too sure if I'm going to have it on your assignment, but if it's easy enough, then I'll definitely add it. So oblique asymptotes are straight lines that are slanted to which a function becomes increasingly close. They occur with a rational function in which the degree of the numerator exceeds the degree of the denominator by exactly 1. Okay? To determine the equation of an oblique asymptote, divide the numerator by the denominator. The resulting quotient is the equation of the oblique asymptote, so a linear function. So we're basically using synthetic division. So we want to determine the oblique and vertical asymptotes of f of x is equal to 2x squared plus 3x minus 1 over x plus 1. So our vertical asymptotes have to do with my denominator. So I know right away that my vertical asymptote is that x is equal to negative 1. So I'm going to go down to my graph, and at x is equal to negative 1, I have a vertical asymptote. Now, I need to determine what happens after that. So I need to check if my divisor, which is x plus 1, is an actual factor of my numerator without giving me a remainder. So we're going to use our remainder theorem. So we're going to sub in p of negative 1, because remember this is p of x and this is q of x. So I need to determine if this gives me a remainder or not. Which gives me 2 minus 4, which is giving me to negative 2, which does not equal 0. Okay, so it doesn't divide into my numerator perfectly, which is perfectly fine. So now let's check out my limits. So let's check out if my limit as x approaches negative 1 from the right of f of x. We get it approaches negative infinity. And the limit of x approaching negative 1 from the right of f of x, it gives me positive infinity. So now I need to check for my oblique asymptote. So we're going to use synthetic division, which is something you guys like. So what is my factor that I can use for my denominator? What's my factor in the denominator? So it's negative 1. So again, synthetic division, set it up. 2, 3, negative 1. You already know that I'm going to get a remainder, which is fine. But I just need to figure out what my oblique asymptote is going to be. So remember, when we do synthetic division, we drop the degree by 1 each time. So my oblique asymptote is going to be y is equal to 2x plus 1. So what that's going to look like is my oblique asymptote passes through here. So this is y is equal to 2x plus 1. Yeah, it's called a slant, but it's also called oblique because it's not a horizontal or vertical line. It's just weird. So now let's find my x-intercepts, where we set y is equal to 0. And we're just focusing on my numerator for this. So I get 0 is equal to 2x squared plus 3x minus 1. I cannot factor it properly because I don't get a product or sum. It doesn't work out. So I have to use my quadratic formula, which you guys have now used since grade 11. So I get x is equal to negative 3 plus or minus the square root of 17 all over 4. So I get x is equal to about 0.3, or x is equal to approximately negative 1.8. So I get over here, negative 1.8 somewhere here. And I get 0.3, which is somewhere here. Now for my y-intercept, I can set x is equal to 0 for f of x. So f at 0, I just get negative 1 over 1, which is equal to negative 1. So my y-intercept happens at 0 and negative 1. So now I have to figure out my end behaviors. This is the only bad thing about these questions, that you have to do a crap ton of work just to figure out how to sketch the graph properly. Okay, so with oblique asymptotes, I have to sub a really big positive x value for my original function and then for my oblique asymptote function. So let's sub in f at 1,000 for my regular function, which is the rational, and I get approximately 2,000.99. So if I have my oblique asymptote, let's sub in y at 1,000 for 2x plus 1, and that gives me around 2,001. So which means that 2,000.999 is less than 2,001. Which means that my f of x is less than my oblique asymptote, which means that it is below my oblique asymptote. So as x approaches positive infinity, it approaches 2x plus 1 from below. Okay, so what that means is I am below my oblique asymptote, which means I'm going to be under it as I get farther to the right of my x values, which means that this part of the graph is probably going to look something like this. Because as I go towards my positive x values, as I get closer to positive infinity, my graph is always going to be below my oblique asymptote. And I need to figure out for my negative infinities. So let's try f at negative 1,000. That's going to give me negative 1,998. And now let's sub in for my oblique asymptote at y of negative 1,000. And that's going to give me negative 1,999. So my f at 1,000, negative 1,000, is already bigger than my oblique asymptote, which means that it is above my oblique asymptote, which means that the limit as x approaches negative infinity of f of x is equal to 2x plus 1 from above. Which means that my graph is always going to be above my oblique asymptote at all times.